Hello and welcome to the Bulletalks podcast, where we explore anything and everything related to STEM. Let's start a little differently today. Instead of thinking about plastic as just an object, let's think of it as a timeline. A plastic wrapper might be used for 5 minutes, thrown away in seconds, but remain without degrading in the environment for hundreds of years. That mismatch in time is at the heart of the plastic pollution crisis. So today, rather than asking how bad plastic pollution is, we are asking a more forward looking question. Can science redesign plastic's entire lifespan? From creation to disappearance? With new innovation, the answer is beginning to look like yes. Our story begins at the stage where plastic usually fails us recycling. Most recycling today is mechanical. Plastics are sorted, melted, and reshaped. Each time this happens, the long polymer chains that give plastic strength, they shorten, weakening the material. After a few cycles, that plastic becomes absolutely unusable. This limitation is why so much of recyclable plastic still ends up as our waste. To overcome this, scientists developed chemical recycling, and one of the most promising methods within this category is hydrochemolytic processing. This technique uses controlled chemical reactions and simple catalysts reacting with water and hydrogen to break plastics like polyethylene and polypropylene down at the molecular level. Here, they help split polymer chains into their smaller hydrocarbon molecules without burning them. The result is a refined oil like substance that can be reused as a raw material to create new plastics, industrial chemicals of near virgin quality, and even fuel. Instead of degrading plastic through repeated melting, this method essentially rewinds it back to its chemical origins. Now, let's shrink our focus from industrial reactors to the microscopic world, where biology steps in. Some bacteria naturally produce enzymes capable of breaking specific chemical bonds. Enzymes are biological catalysts, proteins that speed up biochemical reactions with incredible precision. Researchers discovered enzymes that can degrade common plastics such as PET and then began engineering them to work faster, survive harsher environments, and target additional plastic types. What makes enzymatic degradation so powerful is its selectivity. Instead of shredding plastics into microplastics, enzymes cut polymer chains into their original monomers. These monomers can then be reused to make new plastic without losing any of its quality. This process consumes far less energy than traditional recycling, avoids releasing toxic byproducts, and is immensely quicker. In simple terms, enzymes carefully unlock plastics to gather their monomers for reuse. Scientists then took this idea a step further by combining enzymatic degradation with genetic engineering, particularly using CRISPR technology. CRISPR allows researchers to precisely edit DNA molecules and change cell functioning. By modifying microbial genomes, scientists can enhance plastic degrading pathways in enzymes or introduce entirely new ones. These engineered microbes can even convert the resulting molecules into biodegradable polymers or useful chemical intermediates. Can you imagine? This approach falls under bioremediation, which is the use of living organisms to clean up environmental pollutants. In this case, plastic waste becomes an input for biological manufacturing rather than an endpoint. Plastic is no longer treated as garbage, but as a carbon source that biology can repurpose. But while degradation tackles solid waste, another invisible threat with plastic remains microplastics. Microplastics are fragments smaller than 5 millimeters that easily pass through filtration systems and accumulate in water bodies. To address this, researchers developed advanced hydrogels, materials made of three-dimensional polymer networks capable of absorbing large volumes of water. These hydrogels are engineered with molecular structures that selectively bind microplastic particles. Once captured, exposure to ultraviolet light initiates chemical reactions that degrade the trapped plastics. What makes this system especially elegant is its afterlife. When the hydrogen can no longer function, it can be converted to carbon based materials that absorb other pollutants, such as heavy metals. So the cleanup material itself becomes a part of another environmental solution. Finally, let's step away from recycling and degradation and talk about replacement, a true alternative to fossil based plastics, known as arboform, sometimes called liquid wood. Arboform is derived from lignin, a natural polymer found in plant cell walls that gives wood its rigidity. Lignin is often a waste product of paper processing, but here it is repurposed into a moldable thermoplastic like material. When heated, arboform can be injection molded, much like conventional plastic, making it compatible with existing manufacturing systems as well. What makes this option stand out from other sustainable competitors is its life cycle. Lignin is renewable, biodegradable, and carbon rich. Products made from it do not fragment into microplastics and can naturally reintegrate into the environment. In performance terms, Arboform offers high stiffness, good thermal resistance, and electrical insulation properties, allowing it to be used in electronic casings, automotive components, and consumer products like you and me use every single day. In a way, this material flips the story completely. Instead of forcing plastic to behave like nature, our nature becomes the plastic. So here's the question to leave you with. If plastics can be chemically reset, biologically digested, filtered from water, and even replaced with plant based alternatives, what does responsible material use actually look like going forward? The technologies we explore today don't promise a plastic free world. They point towards something more realistic and more powerful. A world where materials are designed with their entire lifespan in mind, where waste is temporary, not permanent. Plastic pollution wasn't caused by lack of innovation, it was caused by incomplete thinking. What we're seeing now is science finishing the job.